So math counts week 2, exponents, okay? So every day before class, I'm going to go over the topics. So today's topics are, first of all, the exponent rules, and then we have an application called trailing zeros, and then we're going to go on to a ton of math counts problems from the math counts competition, okay? So here we have the exponent rules, and most of you should have seen this before based on how you did during the placement test. So as you can see here, we have these rules that decide what happens when we multiply, divide, and take exponents to a power, okay? So these are the rules that you're going to be using for exponents, and I think most of you should know these already. And if you don't know these, then you can take a screenshot or whatever to give you a better idea of how exponents work. And one good way I like to memorize these is that if we look at the order of operations, we know that's PEMDAS, right? PE and then PEMDAS. And then they're like on levels. So the parentheses is on its own level, and then multiplication and division, they're on their own levels too. Okay? So if we look at this, we see that outside of the exponent, there's a multiply. Inside the exponent, there's a plus. So it's moved up from this rank, it's moved down from this rank to this rank, right? Multiply, inside the exponent, turn into a plus. Divide, inside turn into a negative, still going down. Now we have a power, which is an exponent. It turns into multiplication, so it's going down again. So the pattern here is that whenever we put an exponent and we combine them into an exponent, like here, these are separated, now we put them in one exponent. When we put them in one exponent, then it kind of moves down one level. It went from exponents, here it went from exponents to multiplication, division to subtraction, multiplication to addition, okay? So that works for these three rules, and then the other rules, these two rules, they're basically the same. This is basically the distributive property. Okay? You can distribute the exponent. This x can go to a, this x can go to b. And then you have a to the x times b to the x. Same thing for here. The x goes to the a goes to the b, a to the x, b to the x. Okay? So these two rules are just the distributive property. And then we have the zero rule. This is basically just memorization. Anything to the 0th power is going to equal to 1. But why? Have you ever wondered why? Well, let's write out some powers of 2. We go from 8, 4, 2, 1, and we go to 1/2, 1/4, 1/8, etc. Okay? Because every time we're dividing by 2. Divide 2, divide 2. Okay, so that's why these are multiples of powers of 2. So the 8 is 2 to the 3rd, 4 is 2 squared, 2 is 2 to the 1st, and then we divide by 2 on the number 2 to get to 1, which is 2 to the 0. And this works for any kind of power. If we go from 9, 3, we're dividing by 3. This is 3 squared, this is 3 to the 1. If we divide by 3 again to get to the next number, we get 1, which is 3 to the 0. Okay, and if we go even further, we get 1/3, which is 3 to the negative 1. And this comes to the last rule here, is that if we take the negative exponent, it doesn't make the number negative. It just takes the reciprocal of the exponent without the negative. So if I had 3 to the negative 2, then it's the reciprocal, which means we take 1 divided by 3 squared. Okay, this is the same thing. So the negative doesn't make the number negative, it just turns it into a fraction. Okay, so are there any questions about the exponent rules? All right, so the exponent rules are basically the general rules you're going to be using for exponent problems, and you're just going to have to apply these rules to simplify complex expressions of exponents. So let's do like a few problems here. So these are pretty simple, and they're just basically following the exponent rules. So if the sum numbers are too big, then just write them as an exponent. Four more minutes. How about 2 more minutes? So I'm going to explain these now. So for the first one, it seems like we could just divide 40 to the 3 minus 1, but we can't, right? Because there's a 1 on the 16. But the exponent rules say that the bottom number, the big number inside the exponent, has to be the same for you to do all these operations with it, okay? So you have to get these numbers to the same base. We call it the base because it's the biggest number, it's the base. We have to get them to the same base before we can do all our exponent rules. And remember how 40, we can break down 40 into 8 times 5. And this is going to the third. 8 times 5 to the third, we know that we can distribute the 3. So we get 8 to the third times 5 to the third. This is divided by 16. Well, they're still not related. But 8 is a power of 2. 8 is 2 to the third. 16 is also a power of 2, 2 to the fourth. So we can replace these with 2 to the fourth and 2 to the third. Remember how this is 2 to the third power. Okay? So now we use the power to a power rule, and this is equal to 2 to the 3 times 3. 2 to the 9th. Okay? So now we have 2 to the 9th divided by 2 to the 4th. So we can do 9 minus 4 to the 5th. Okay? And this is your answer. You could basically leave it like this if you didn't want to expand it out. But if you did, it should be around 4,000. Okay? So now for the next one, same thing. We have to get them to the same base before we can do any exponent operations on them. So how to get them to the same base? Well, 9 is a power of 3. 27 is also a power of 3. So let's replace those. 9 is equal to 3 to the power of 2. 27 is 3 to the power of 3. So we're going to have 3 to the 17 times 3 to the squared to the 4th power, because we're replacing the 9 in there with 3 squared. And this is multiplying by 3 to the 3rd to the 10th power. Now we do power to a power. This is 3 to the 2 times 4, which is 8. 3 to the 8th. Now the next one is 3 to the 3 times 10, which is 30. Now since they're all multiplying, we just add up the exponents. 17 plus 18 plus 30 is 55, so it's 3 to the 55th power. Okay? Next one. This is a lot more complicated. So let's first deal with the stuff that's in the parentheses before we decide doing the -3 power. Okay, so first of all, we can break down 63 into 7 times 9. So basically the trick in doing exponents is to try to break down all the numbers into like the simplest possible form. Okay, 63 is 7 times 9, so it's going to be 7 times 9 squared over 49 times 3 to the 6th. Now we can distribute the exponent, so we get 7 squared times 9 squared. 7 squared times 9 squared. Well, 7 squared is 49, so these are going to divide out to equal 1, so they don't really matter anymore. Now I just got 9 squared over 3 to the 6th. Well, we can't do this just yet because we have to get them to the same base, right? So how to get 9 in the same base as 3? Well, right here, 9 is 3 squared, so let's replace 9 with 3 squared. 3 squared squared over 3 to the 6th. Power to the power is multiplying, right? So we got 3 to the 4th. 3 to the 4th over 3 to the 6th. If we divide, we subtract the powers. 3 to the -2 power. And all of this is going to be equal to inside the parentheses. So now you got to apply outside the parentheses. Well, this is still a power to a power. It doesn't really matter if they're negative or positive. So -2 times -3 is just 6. 3 to the 6th. And that's your answer. Okay. The last one. Well, when we do math, we don't really like to see this symbol. This symbol, it doesn't really mean anything, right? So division is fractions. So we can rewrite this as all of this junk over 32, because it's in the parentheses. Okay? So all of that over 32. So now what do? We know that we can distribute the 32 to each of these, but we can't just divide them just yet. We got to get them to the same base, right? And all of these are in bases of 2. So let's try to get 32 into a base of 2. Well, 32 is 2 to the 5th. Okay, so now we can distribute it. 2 to the 5th, to the 8th divided by 2 to the 5th, that's 2 to the 3rd, which is because we subtract the exponent. Then we do this one, to the 4th, do this one, to the 5th, do this one, to the 6th. 2 to the 3rd plus 2 to the 4th plus 2 to the 5th plus 2 to the 6th. Well, we're adding these exponents, so we cannot do anything to simplify this anymore. But we can just add them together because these numbers are entirely feasible, right? 2 to the 3rd is 8, plus 16 plus 32, plus 2 to the 6th, which is 64. So these are not that big of numbers, so you can just add them together, and you should get 120. Are there any questions? Cool. So now we've got a common application of exponents, which is trailing zeros. So the example problem is, how many trailing zeros are 3 to the 5th times 2 to the 13th times 5 to the 10th? So first of all, what do trailing zeros mean? Trailing zeros means how many zeros are in the back of a number. For example, we might have a really big number like 600, like this. When we say trailing zeros, we're going to look at the zeros that are at the end of that number. So we're going to say these are the trailing zeros. 1, 2, 3, 4, 5, 6, 7, 8. 8 trailing zeros. Okay, if this number were 107 with a lot of zeros behind it, this zero is not a trailing zero because it has a 7 after it. So we're only going to take the zeros at the end. It has to be a long stretch of zeros. Okay, so in this case, we're going to have 5 trailing zeros. So those are what trailing zeros are. So how do we find the trailing zeros in such a big number without multiplying it out? Well, you know how when you multiply anything by 10, like 67 times 10, what we basically do is we attach a 0 to the end of 67, right? We all know that. If we attach it to 2 10s, we just attach 2 zeros to the end. So it seems like whenever we have a 10, we add a 0. And those zeros always go at the end, right? Because we never put, we never put the 0 in between the 6 and the 7. We're always going to put those zeros at the end. So whenever we have a 10, a power of 10, so this is 10 squared, right? We have 2 10s, and we have 2 zeros. So the amount of trailing zeros is equal to the amount of 10s we have inside the number. So basically, we want to find how many powers of 10 can we extract out of this? Well, 10 is equal to 2 times 5. So we want to put 2's and 5's together to get the 10. All right? And basically, we can only get 10 from 2 and 5. 3 doesn't do anything to help us find trailing zeros. So that just basically we can throw away because that doesn't really matter for us. All we need to find are the trailing zeros. And to find 10s, we only care about 2's and 5's, right? So how many 10s can we find in here? Well, we can divide up the 2 to the 13th to 2 to the 10th times 2 to the 3rd. This is multiplied by 5 to the 10th. And now we have 2 to the 10th, 5 to the 10th. We can put them together, right? This is the reverse distributive property. If we put them together, we get 2 times 5 all to the 10th power. And we have 2 to the 3rd outside. 2 times 5, we can simplify that in the middle, inside. And we get 10 to the 10th power. And that's how many trailing zeros we have. Okay, so to find how many trailing zeros are in a number, you just have to find how many powers of 10 are in that number. And anything else that doesn't contribute to powers of 10, you can just throw those away. You don't need to consider them at all. All right, any questions? Cool. So 2 trailing zeros problems. I'll give you guys 5 minutes to do these. All right, so how about I explain the first one now, and then that might give you a good idea of how to do the second one. Okay, so for the first one, we want to find how many tens can we take from this number. So, well, 8 times 5, we don't really want that. We want 2 times 5. We want to find how many 2's do we have, how many 5's do we have. So let's turn 8 into a power of 2. 8 is 2 to the third. So this is 2 to the third to the 14. Times 5 to the 32. Well, power to the power, we just multiply them. So it should be 2 to the 42 times 5 to the 32. Well, obviously 5 is the limiting factor here because we only have enough tens as long as we can have a 5 to pair with a 2, right? 5 is like the maximum. So basically, we could kind of prove this by splitting up the 2 to the 42 into 2 to the 10 times 2 to the 32 times 5 to the 32. These two, we can reverse distributive property, 10 to the 32 times 2 to the 10. As you can see here, we only have 32 tens here. And then 2 to the 10th, that's 1024. That doesn't have a trailing zero. Okay? And obviously, that's because it's not a 10, right? So we have 32 tens. So that's the answer, 32. So one person said the answer was 10 to the 32, like this number. And sorry if that confused you. The amount of trailing zeros is how many powers of 10 you have. So we have 32 powers of 10 here. We have 32 trailing zeros, not 10 to the 32 trailing zeros. Okay? So now that you know that, I'll give you 2 minutes to do the last one. Okay, so let me explain the last one. So how many zeros are there in front of this number? Well, if you think about it, this is just the reverse of what we're doing with trailing zeros, right? Because for 1/10, 0.1, that's 1, 0. 1 over 100, 0.01, 2 zeros. Okay, so for every power of 10 we have in the denominator, that's 1 extra 0 in front of the number. Okay? So we want to find how many powers of 10 are there in the denominator. Well, that's not that bad, right? All you have to do is find the amount of tens in this number. 25 to the 8th times 20 to the 5th. First of all, we already have tens in 20 to the 5th. We can divide 20 to the 5th up into 10 times 2 to the 5th. And then that's 10 to the 5th times 2 to the 5th times 25 to the 8th. We already have 5 tens. Okay? So we already have 5. Now we can take this away. How many tens left do we have in the other part of our answer? Well, how many tens can we make from these? Well, it seems like in this number, this is 5 squared. 5 squared to the 8th, 16 fives. So it's going to be 5 to the 16 times 2 to the 5th. Obviously, there's not enough 2's to sustain the amount of 5's. So 2 is the limiting case. So we're only going to have 5 tens possible from this group. So we had 5 from the initial 10. Now we have 5 from this group. 5 plus 5 equals 10. Equals 10. And that's the answer. There are 10 zeros in front of the number because we found that for every power of 10 in the denominator, there's 1 0, 2 zeros, etc. Okay? I've got math counts problems. These problems are from the math counts competitions. Okay? So the second one should be pretty straightforward because you just learned how to do that. So yeah, I'll give you 5 minutes for these. And once you get your answer, you can chat that to me, and I'll tell you if you're right or not. So for these problems, first of all, for the first one, you can see how you could just write all of these out as powers of 2, right? 2 to the 2 squared times 2 squared to the squared times 2 to the third to the squared. But that's a lot of math, you know? Why do you have to multiply 2 for every single one of them, right? So what can we do here then? Well, all of them have powers of 2 on them. So we can take the 2 out. We can distribute the 2, reverse distribute the 2 out of everything. So it's just 2 times 4 times 8, dot, 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 times 1024, all squared. So if we find this as a power of 2, then we can just multiply that power by 2. Okay, so that makes it a lot easier for us. So 2 is just 2 to the first, 2 squared, 2 third, all the way to 1024, which is 2 to the 10th. Okay, so since they're all multiplying, all you do is add the numbers from 1 to 10. And that shouldn't be that hard, and you should get 55. So this is going to be 2 to the 55 to the second power. But this is not the simplest form just yet, because it wants it as a power of 2, nothing else, okay? It just has to be 2 and some other number. So we're just going to use power to the power here, multiply these, 2 to the 110. And that's the answer. All right? So you got to read really careful here. First of all, if you get the answer, but it's not in the form that they want, they're going to count it as wrong. And that's the bad part of math counts, okay? So now for the second one, this is basically a trailing zeros problem. But the trick here is that it says how many digits in total. So how do we find that? Well, if we find how many zeros there are, then those are digits, and then we have some other number left over, right? If we find how many digits are in that number left over, then we can add the digits together and find our answer. So first of all, how many trailing zeros are there in this number? Well, you got to turn 8 into a power of 2, right? 2 to the third, 2 to the 10th, times 5 to the 22, 2 to the 30th, times 5 to the 22. Okay, so let's split the 2 into 2 to the 22 times 2 to the 8th is 5 to the 22. Now these two we can reverse distribute, and we get 2 times 5 to the 22 times 2 to the 8th. This is a 10. This is 10 to the 22. Erase this. Since we have 22 powers of 10, then we have 22 trailing zeros. So we already have 22 digits that are just zeros. And then we have, after we have all those zeros, then we have some number in the front that equals this. 2 to the 8th, well, that's 256. 3 extra digits, so we just add 325. All right, any questions? Cool. 2 more problems from the math counts. This one is also highly linked to trailing zeros. I'll give you 5 minutes for these. one more minute. Okay, so for the first one, I'm going to find the sum of the digits in this huge number here. So we're going to have all the digits and we're going to have to add them together. Well, obviously you can see that we have many powers of 2, many powers of 5. So if we put them together, we're going to have many powers of 10. That means this number has a lot of trailing zeros. So there's going to be a ton of zeros at the end. And the thing is, these zeros don't do anything to add to the sum of the digits, because if we just add these zeros together, they really don't make any difference, right? So if we just take the trailing zeros out of the equation, and then we just focus on the numbers that aren't zeros, we just need to add them together. All right, so first we need to find how many trailing zeros there are. Well, 5 to the 2007 can be split up into 5 to the 2005 times 5 to the 5 to the second, multiplied by 3. Okay? These two, reverse distributive, 2 times 5 to the 2005, 5 squared times 3. All of this is trailing zeros right here. So it does nothing to add to our sum, so we can just ignore all that. All we have left is 5 squared times 3. That's just 25 times 3, which is 75. All you do is add these two digits together, 12. Okay? Next one. Well, it was a lot like the first problem on the last slide. Since there's a power of 2 on all of them, we can basically take them out because they really don't make any difference. All right, so all we have left is 22 times 5, 55 equals 10 times n. Okay, so all you need to do now is divide 10 on both sides to get 22 times 55 over 10 equals n. And you could just multiply these out straightforward, and that wouldn't take that much time. But if you want to be really efficient, then you turn 22 into 2 times 11, 55 into 5 times 11, and all of those over 10. 2 times 5 is 10. Well, these go away. 11 times 11 is just 121. Okay, so that's the answer. Any questions? Cool. So I have two challenge problems here. They're basically the same thing. So I'm going to cross out the second one, leave that for homework. And you guys should do the first one. Once again, all these problems are from the Mathcounts. They're taken from the Mathcounts competition. One more minute. Because if you know the trick to this problem, then it should be pretty easy. Okay, so I'm just going to explain this now. So the thing is, we can take the n to the 2000. The 2000 is really a really big number, right? And 5 to the 3000 is just as big of a number. So we can split this into n to the 2 to the 1000. This one is 5 to the 3 to the 1000. And since we're comparing these and both of them have 1000 power on them, the 1000 power really doesn't matter at all. So now we're just comparing n squared and 5 to the third. 5 to the third is just 125. So what is the largest n, which is less than 125, so that n squared is less than this? Well, it's just 11, because 11 squared is 121. And that's the answer. Okay, and the next one is very, very similar. Basically the exact same strategy. All right? So that's it for today, okay? So I'm going to send out the homework later, and I hope you enjoyed this class. All right, I'll see you guys next week.